Welcome back. In this video, we're going to be moving on to our next topic, in which we'll be looking at internal forces of members, such as beams or frames or things like that. Now, just to kind of recap where we're at and what we've been working on, okay? Since we started our study in statics, we've been kind of following this basic statics progression idea. So I want to kind of recap this for us and be able to kind of look at the progression that we make, mentally, as we look at how can we tackle problems, or what tricks and techniques can we look at. Because once you get the vectors down, this whole process is all about solving a puzzle, figuring out, well, how can I find a specific piece of information, or what tricks or tools do I have at my disposal to be able to do that. All right, so if you remember, the first thing that we always looked for was we did nothing. We took a whole system and kind of identified, maybe it's a structure that looks something kind of like this, and we tried to figure out, well, is there any information that I can gather off of this particular piece, right? And so if we went through, remember, we're looking at our Y's again, okay, as our rules for constructing a free body diagram. W is the weight, I is internal, S is support reactions, and E is our external forces. So if this is my structure, this consists of a ring at B and a rope, that connects, a pin at A to the ring, and then another rope that connects the ring at B to another pin at C, and then those two together are holding up some weight W. If we look, okay, and we try to figure out, well, what can I look at, or what can I solve out of this particular problem? Now, if you remember, for us, we would have an AY here, and an AX there, and then I would have a CY here, and a CX there, okay? And if you look at that, assuming that we know the weight W, and we know all the angles and lengths and that kind of thing, this system has 4 unknowns. I have 2 at A and 2 at C, or 4 unknowns, and what we know from statics is we only have 3 equations. So this is statically indeterminate the way that it's currently drawn. Okay, so that becomes a problem. If I have more unknowns than I do equations to solve them at my disposal, that's an issue. So we start looking at, okay, well, what do I do in this case? Now, sometimes you get lucky on the full system, and maybe I can find 1, or maybe I can find 2, depending on how certain things lay out. Horizontal beams, you can often find the verticals on those, but if things are at a slope, then it gets a little bit uglier and a little bit harder to do. Right? So we start thinking, well, what tricks do I have at our disposal? And we start kind of going down this checklist that we're going through here. So the next one that we look for is, are there any ropes or cables? Because we know that a rope, if I cut it, I can extract out the 2 unknowns at the end, right? And I can replace them with a single internal unknown, such as the tension of the rope. And we do know that ropes and cables, they're tension only. I can't have compression. There is no bending. Okay, so everything is a rope. So if I were to come through then on this particular problem and maybe cut this rope and cut this rope, I now get a picture that looks something kind of like this. Okay, and so now I have my ring at B, and I have this internal force that we cut in the rope over here. There's now a tension, TAB, and then if I cut the upper rope, I now have this guy, TBC. Now again, obviously he's moving at some angle theta, because I'd have to know his orientation, and then I know that the weight W is a gravity load acting down. I now have a new free body diagram, all achieved by cutting just the ropes and the cables. Okay, and in this case, now I only have 2 unknowns. Okay, and so now we've taken the system and made it back to being statically determinate. All right, and what I can do then is that if I look at the wall, okay, and if I put my AY here, and I put my AX, okay, and I leave that little bit of a snippet of a rope and I've cut there, okay, we know that the tension that was here from the rope on the ring has to be met and balanced by a tension there, okay? And so what I've done is I've basically taken a free body diagram and split it into 2 smaller ones. And then I can do the same thing up at C as well. Okay, so if I can find TAB, which you could do that, doing sum of forces X and sum of forces Y, I can turn around and say, well, I know this TAB, and then I could do forces X and forces Y on this guy and pick off AX and AB, or an AY. Okay, so ropes and cables are a pretty valuable trick, okay? Now, sometimes, what do we do if we don't have a rope or a cable? And that led us to our next topic, okay, which was 2 force members, okay, and these were more specifically the trusses. Okay, now a 2 force member had a set of criteria that we had to have. Okay, the first one was I had to have a straight member. Okay, it had to be pinned at the ends. Okay, and then it also could only be loaded at those ends, at those joints. Okay, and if I did that, then we had a couple of tools or tricks at our disposal to be able to find those. Okay, I could do the method of joints, I could do the method of sections, and so on and so forth. Okay, the thing that we knew though was that and this was apparent in the methods that we're looking at, is that whenever I cut my truss section, okay, we either had an axial tension or an axial compression. Okay, now again, compare that back to the ropes and cables that it was tension only. So this is getting a little bit more complex. Okay, and so we had some tricks on how do we solve these, doing method of joints and method of sections. I'll leave the review of that as an exercise for you. We've got some videos on those, so if you need to take a look at those. Okay, all right. Now, after that, we then progressed into frames and machines. Okay, and these were systems, and typically we denoted a frame and a machine as a system of members that didn't necessarily have to be straight. Okay, but could be hinged, at certain locations. They were always connected by a pin that connected multiple pieces. And if that was the case, then we could take advantage and go look for our, pin forces between those, and we would be all right. Okay, so if I took it just a simple system, well, this guy here may be a truss member, it's straight pinned at the ends, and there are no loads, so that would be a truss member. I know this guy is axial, but say I didn't. Say this guy had, some force P happening here, that over on this guy here, okay, and then I had a moment on this non-straight member. Okay, this is clearly not anything that we've seen in the upper parts of the list. Okay, so the methodology is you start looking for pin locations, and we look to separate things into pieces. Okay, and so if I kind of come over and I look at this, so here's that elbow piece, right? And so I had my supported A, so it's a pin, so AY and AX. We had our moment. Okay, now if you remember, here was AY, here was AX. Let's call this CY, and this is CX. We're back in the same system or a situation where I have a structure with some complex loading on it that has four unknowns. It's statically indeterminate to the first degree. All right, so the idea was that I could take this thing and I could blow it apart and get a free body diagram that looks like this. So we've talked about A, we've talked about the moment, and then up at the pin, we had two unknown forces because this guy is connected to a pin which is connected to another member, that there's some vertical force and some horizontal force that has to exist at that location. Okay, this piece pushes on the pin pushes back. That's the arrangement, okay? And then if I go look at the other piece, I have this diagonal, okay, and I have BX2 and BY2 are the forces that this member makes on the pin, okay, and then I pick up CY and CX, and of course that point load in the middle for us there, okay? The one piece that makes all this go for frames and machines is the behavior of the pin itself, okay? Because remember, I assume this guy pushes on the pin. Well, Newton says that for every force, there's an equal and opposite reaction. So if this pushes on the pin pushes back. And so this is what this is saying. Okay, so my BX1 is in the opposite direction of this guy. My BY1 is in the opposite of this. And same for BX2 and BY2. And now this is a valid free body diagram that I can look at. And I can now say that, oh, well, I know that this guy and this guy, if I write sum of forces X equal to 0, I know that those two guys have to be equal and opposite. And I can do the same thing on the pin and do sum of forces Y equal to 0 and say that these two guys have to be equal and opposite in order to maintain equilibrium on that guy. Okay? All right. Now, what happens when none of this is the case? Okay, now, in our frames and machines, okay, we were only able to go in and find the forces that were happening on the pins. But say I wanted to know what was going on in this member here so that I could design that to be big enough to hold the loads. Okay, we don't have the tools to do that with any of the methods that we've just looked at. Okay, now I could probably pull something off here using some of my earlier tricks for tension and compression and go for that, but this is a bit of a problem because this is a more complex system. It's not experiencing just axial loads anymore. There's other things going on. Okay, and that's the case where now we've left, the problems that we know how to solve, and we're moving into a kind of a more general realm. Okay, and this is classified as what we call internal forces. Okay, or more specifically, internal moment, shear, and axial forces. All right, so that's kind of a rundown of where we're at. Okay, and it gets progressively more complex, and we're limited on things that we can do. So, if we look at this, okay, let's just take, internal forces, and we're going to look at our shear, moment, and axial. Okay, and so let's just take just an arbitrary, simply supported beam. It's pinned at A, roller at B. Okay, and I've got some arbitrary distributed load. So this is a W as a function of X. Okay, and then I've got 2 point loads acting on this thing, a P1 that's got a horizontal piece It's kind of acting at this angle theta, and I have a P2 that's vertical at whatever their position is, all right? Okay, let's suppose that, I'm the engineer that needs to design this beam to be big enough to hold the loads. Okay, well, obviously, I want to be able to design for the worst possible effects. Now, the issue that we have with this, and one of the reasons we have to go through all this, is I don't know where the worst is in this. I could take a blind guess and say, well, let's just try here and cross our fingers and hope it's right. But, as engineers, we like to be a little bit more confident in what we're doing, that we've found the worst possible case. Okay, so what we can do is we can go in and we can, let's just say, to reveal what's happening here, this is an internal effect. So to reveal internal forces, we have to cut it to reveal them. All right, and so if I do that, and I kind of show you what happens on this particular piece. So what I've done is I've cut it at this dotted line, and I've kind of blown it up a little bit so we can see what's going on. Okay, so this becomes my free body diagram if I look at doing everything inside of that little boxy region. Okay, this would be the piece that would come out of all of this. All right, now that's a free body diagram. Okay, and so we apply our y's. So we've got our weight, our internal. Now internal show up when we cut, and so this was my cut line. So the question that we have is, what's going on here? All right, I've got all my external stuff. I have my support reactions. There should be an AX here. Okay, what's happening in this effect? Okay, and so if we look at this, okay, let's just start and let's just go with writing our equation. So sum of forces in the X equal to 0. Okay, if we go in and we look at these particular forces on this, we know that we have AX plus P1 cosine theta plus whatever's happening at the cut has to be equal to 0. Okay, now for this, we know, depending on what the load is doing, I don't know what is happening at that interface, but I do know that it's possible that there's some force that shows up, okay, that would be acting maybe either in this direction. Again, we're going to draw it as a tension force. Okay, we're going to call this as N. Okay, and N is an axial force, but more specifically, it's a normal force. Okay, it's normal to the cross section, meaning that the angle between N and the angle between the cut is 90 degrees. This is just like what we did with trusses and what we did with ropes and cables. All those axial forces were this N guy that were happening on this. Okay, so it's potentially possible that I have some non-zero N value that shows up on this. Okay, I could go in and do sum of forces in the Y on the same picture. Okay, and so we'll go up positive. We were to the right positive on this one. Okay, and so my equation now is AY, okay, minus P1 times the sine of theta, okay, minus, we've got this weird distributed load thing, so we would just do the integral of Wx dx to find out whatever that load is as some general effect, okay. But then if that's the case, if I have an AY value in these, it's possible that this doesn't itself add up to 0. So what we're going to do is we're going to add some internal effect here that represents what's happening at the cut. Okay, and this one's a little different, and I'll explain the sign convention here in a second, but we're going to draw him down, okay, on that particular cut location. All right, and so this V then, if you look, V is what's known as a shear force, okay, and it's parallel, okay, to the plane that we cut. So we cut here, okay, and this term shear and normal will become very, very important when you get into your mechanics and materials studies, in that these will dictate normal stresses and shear stresses. These are the two guys that will start to do this. So in order to do anything after statics, I have to know these guys, okay, and so that's why this step is so critical. Okay, now if we look at everything else that's happening, it's almost apparent that if I do a sum of the moments at that cut location on there, I get some AY times a distance X, plus whatever the P1 is doing times its perpendicular distance, plus whatever the WX is doing times some distance there, and so forth and so on. Now, again, not getting too far ahead of ourselves, there's a whole lot of stuff causing a moment in this thing, and it's highly likely that the moment caused by him plus the moment caused by him plus the moments caused by all of these guys will not add up to 0. And if that's the case, then that means that there has to be something there at that cut location in the form of a moment at the cut. Okay, and so the M is our moment. All right, so what happens, and so this gets a little a little ugly, all right, for us. Now, it's not necessarily overly difficult, but what if you have a really big structure? You know, maybe it's, you know, a multi-portal frame on us, you know, that's fixed at the bottom. It has some sort of horizontal force. It might have some verticals on this. My pencil just died. Some sort of there, and I decide I want to know what's going on in the columns of this upper floor. Okay, what this means is that at every location that I cut, if it doesn't satisfy a rope or a cable or a two-force member or a frame and machine, whenever I cut that guy, you know, maybe that's the cut of the upper piece that we're looking at. At every location, this was a cut in order to be able to pull that piece off. Now, I do pick up this point load. Let's call that P1, and let's call this is P1. But at every location, switch pencils here. Right, that there's a moment, a normal, and a shear. And then there's another moment and a normal and a shear. And another moment and a normal and a shear. And at every location that I cut, I now have 9 unknowns on this particular picture. And the more columns I cut, the more unknowns that I get. All right. So these are the internals that we're exposing when I cut across this particular line. All right, so you can see that in a hurry, if I start getting just really sloppy and in a hurry on how I start cutting things, I can make a royal mess that there's no possible way that I can solve with just using statics. Okay, this becomes highly indeterminate because that free body diagram still only has 3 equations. Okay, and so I've made this now 6 degrees of indeterminacy. Okay, and that's a problem. Okay, so we've got to be very careful with how we start to explode this and proceed in a logical setup. So that's kind of the nature of what internal forces are doing and how we're starting to kind of look at those. All right. Okay, so we will stop there for just kind of the basic setup of what we're looking at. And the next example will show you some calculations and kind of show you kind of some behaviors that we're looking at, and that will lead us into some of the tools and techniques that we can start to use. All right, but I don't want this video to get too long, so we'll stop there. As always, please leave a comment in the comments below if there's anything we can do to make these videos more clear, or if you have any questions, please leave a comment and I'll be happy to get back to you. Thanks. Bye.